Hi everyone, Mr. Lee here. In this video, we're going to go over the conservation of energy. Alright, so the conservation of energy is one of the most important topics that we can discuss here in physics. It is one of the biggest reasons that we know so many things about our universe, and it's one of the laws that governs our universe, and we have to follow it to the T. So conservation of energy is simply stated that energy cannot be created or destroyed. All right, now you might have heard this before, right? You can't create or you can't destroy energy, but I'm going to add a little caveat, and that's because our class will focus on this: only transferred. Okay, so the conservation of energy states that energy cannot be created or destroyed, it can only be transferred in one form to another. All right, so with the conservation of energy out of the way, there's a couple of terminologies I want to go over. First off is this idea called mechanical energy. So capital ME is mechanical energy. Now in the previous videos, you might have heard me talk about mechanical energy before, and the types of mechanical energy that we will cover is kinetic energy and potential energy. Now there is potential spring and gravitational potential, so I'm going to add both. Both are forms of mechanical energy, and this is what we're going to be focusing on. We're not going to focus on chemical energy, we're not going to focus on heat or anything like that in terms of mechanical energy. So mechanical energy is just kinetic energy, gravitational potential energy, and spring potential energy. All right, so the equation of the conservation of energy, for us at least, it'll be the mechanical energy initial is equal to the mechanical energy final. Now that right there, that equation is the big equation overall, and that will help us go forward with whatever we need to find out. Okay, so here, like the next couple of steps I'm going to show you, you can skip a lot of the steps if you use a little bit of logic, but the first time you go through these problems, I highly suggest that you don't skip anything and you just follow all the steps step by step, because it does help. Now notice how I put mechanical energy is equal to mechanical energy final. So what we can write here is that the kinetic energy initial plus the gravitational potential energy initial plus the spring potential energy initial is equal to kinetic energy final plus gravitational potential energy final plus the spring potential energy final. Okay, so here we have the equation fully fleshed out. Now, if this is the base equation and this is the equation where it's expanded, you have to actually take a look into the problem itself. Right? So if the problem has moving objects, okay, if it has a spring, and if the object is moving in a height, okay, so with all those three requirements, you have those three forms of energy: motion, height, which is the gravitational potential, and then we have springs. Now, if your problem, let's say it doesn't have springs in the problem, then you don't have to have the spring potential energy. And so our equation can be broken down like this, because there are no springs. Okay, so make this first equation work for you. Okay, you gotta be logical about it. All right. Now, I will tell you that most of the time, this second form of the equation is what we're going to be working with. All right. Now from here we can break it down even more. We can say that 1/2 the mass velocity initial squared plus the mass times deceleration due to gravity times height initial is equal to the final versions of those variables. And in this case, it'll be the final velocity squared plus mass deceleration due to gravity times the height final. Now this might be a lot to write out, but trust me when I say, for these kinds of problems, because we have so many variables all over the place, it really helps if you solve in variable form first and you try to keep things as neat as possible. Okay, so from here, the last thing that we can do is just plug in our variables and solve for whatever we're looking for. Okay, and once again, solving in variable form helps. Now, I'm going to do a little red star, okay, because this is where something is important. When you read the problem, you have to identify, okay, so identify what are your zeros. this helps clean up this very long and very complicated looking equation out very beautifully. So here's what you're looking out for. So if it says a object at rest, okay, that means your velocity is 0. Now you gotta read into it, right, and be like, oh, did the object start at rest or did it end up at rest, right? Because if it starts off at rest, then that means your initial velocity is 0. If it ended up being at rest, that means your final velocity is 0. Okay, but this one's a key one. Anytime it talks about the floor, that means your height is 0. And once again, did we start off at a height of 0 or did we end up at a height of 0? It's up to you to decipher. And I think that's it. We will always have masses within the equation because like we're talking about an object, but these two right here, it will definitely help you identify like what we can cancel out. Now this is what I mean. So let's say that a object starts off at rest. That means your initial velocity is 0. That means this entire factor here, I'll highlight it, this entire factor right there that I highlighted, that all turns out to be 0. Or let's say we have an object that falls to the floor. Okay, an object that falls to the floor. That means your final height is 0 because that's the floor. Oh, and that actually reminds me. If we have a object that is dropped, this is important. If you have an object that is dropped, this goes back to your kinematics unit, and a lot of the kinematics stuff actually comes back here in this unit. If you have an object that is dropped, if there was no initial velocity for that object, your initial velocity in this case would be 0, right? And so that is if you have an object and holding above the ground, okay, it only has gravitational potential energy, and you release it, and so that gravitational potential energy turns into kinetic energy. So here, I'm going to highlight in that case, if you have an object above the floor and you drop it, your initial kinetic energy, that will be 0, and because it reaches the floor, the gravitational potential energy will be 0. So those two highlighted equations will turn out to be 0, which definitely cleans up a lot of the equation itself. Okay, so here are a couple of things to look out for, and there might be a little bit more, but definitely look out for what can be canceled out, what can be considered to be 0, so that you could just cross it out so that you don't have to have this giant equation all the time. Okay, but definitely start here and then start crossing out for the zeros. All right. Next thing I want to go over is a energy graph. Okay, so a couple of things. The law of conservation of energy states that energy cannot be created or destroyed. That's very important. So if we have a graph like so this is the time and this is energy. Now this is energy is of course in joules. Now this is I see these types of multiple choice problems very much. It's kind of like in Newton's third law. Like it's easy to say that for every force is equal but opposite, much like it's very easy to say that energy cannot be created or destroyed, just transferred. And by the way, that transferring, what that means is it goes from like potential or kinetic into like a potential or kinetic, right? That's the transferring. It goes from one form to another. Now it's easy to say that law, but for whatever reason, it's kind of hard to actually apply it. And one of those difficulty comes from graphing. So if we have an energy versus time graph, I'm going to show you what the potential energy and the kinetic energy graph will look like. And so let's come up with a scenario first. Let's say we have, let's bring out that box, right? We have a box up here, and the box is like kind of teetering on the edge, and that box is going to fall. Pew! And it's going to hit the floor. Okay, so in this scenario here, if we were to write out the equation, ME initial is equal to mechanical energy final, and we say, well, there's no springs in here, so I only want kinetic energy initial plus gravitational energy initial is equal to kinetic energy final. Oh, why did I put that E? I don't know. Kinetic energy final plus gravitational potential energy final. Initially, the object was not moving because it's kind of like dropped, so I'm going to cross that out, and hits the floor, so that's crossed out. So our equation looks like this. Okay, and we could break that down even more and say it's like mgh initial is equal to 1/2 mv squared final, right? And so like that's the kind of steps that you should be taking. You should be thinking about the problem, and you should think about, you know, what are my zeros, cross them out, solve an equation form, and then go from it. But this is my scenario. We have an object that starts off here, and we know that it ends up on the floor. So according to this equation, our initial energy, okay, will be potential energy, and we'll say potential energy is red. Now, what happens is, if you remember, when an object is first released, okay, that velocity is 0. And then the acceleration, which is the acceleration due to gravity, will be 9.8 meters per second squared. So it'll start to speed up. It doesn't go fast from the start. It will speed up eventually. And so in order to showcase this, remember, motion is kinetic energy. So if you think about it, in the beginning, it's not moving. So it's all potential energy. And then eventually, it'll get fast and fast and fast. But it doesn't start off fast. It starts off slow, and then it gets faster. To show that, I'm going to draw the potential energy line. We get something like that, okay? Where right here, that's the floor. So you notice how this is this curve. Okay, this curve shows us that it's not moving, and then it gets faster and faster and faster. It's losing that potential energy as it approaches the floor. And so the inverse of it, the opposite of it, will always be the kinetic energy one for a situation like this. So in the beginning, there was no kinetic energy, so I'm going to start off at 0, and then it's going to mirror this, but in the opposite direction. Okay? Kind of right there. All right, so hopefully it kind of like lines up. Okay, so we can see that as the potential energy decreases, the kinetic energy increases, and it kind of like mirrors itself. And so, you know what, I'll put that over here. We'll say that anything in red is gravitational potential, and then anything in blue is the kinetic energy, right? So here we can say that this is kinetic energy final, and this is kinetic energy initial. And here we can say that this is gravitational potential energy initial, and this is the gravitational potential energy final. Okay, so this graph represents this final equation here that we're looking at. Okay, now the final thing, and this is the big highlight, the big kicker, right? The big overall thing. I'm going to draw this a little bit thicker here. Is the mechanical energy. Now, mechanical energy can only change if work is being done to the system, if there's an outside force. And here, there is no outside force. It's just a box. It's just the earth, right? Like no one came in and like punted the box as it was falling. And to showcase this, we have a flat line right there. And this one is mechanical energy. So the total mechanical energy will always be constant. This is very important. This is probably the most important thing about this entire video. The total mechanical energy will stay constant even though the gravitational potential energy is changing. Even though the kinetic energy is changing, this value right here, whatever this value is, it'll always stay the same. And notice how I started off the mechanical energy at the same height as the initial gravitational potential energy, because that's how much energy you started off with. Okay, and notice here that the final mechanical energy is the final kinetic energy final, because that's what it tells us here in our equation, right? Our initial mechanical energy will always be, for this scenario, the initial gravitational potential energy, and our final mechanical energy will always be the final kinetic energy right there. Okay. Now, what this tells us is that if I were to, let's say, get that value, whatever that value is, plus this value, whatever that value is, it'll add up to the total mechanical energy. I'll say it one more time. So whatever this gravitational potential energy is, plus this kinetic energy, okay, when you add these two values, it will always add up to the mechanical energy. You know what? That's so important. I'm going to write that down. Okay. That can never change when there are no outside forces. Remember the shape, and I'm going to go over the shape and why that occurs right now. So the reason why we have this shape is because of the kinetic energy formula, which is 1/2 mv squared. And this v squared right there tells us that the kinetic energy will have a square relationship, and that's what we're looking at right here. And that's that beautiful squared curve that we see. Okay. All right. So if we were to take a look at an object that is being launched from the floor up to a height, so like a reverse of what we just went with, right? So let's say we have a, oh boy, let's make it a little bit straighter. So if we have an object on the floor, right, and then we kind of, I don't know how it got launched up, but it got launched up somehow, right? So it got launched up to up there. So here, if we were to come up with a formula, right, mechanical energy initial, always start off this way. Okay, mechanical energy final. And the reason why I want you to start off this way is because, like, for example, in a free response question, you might get a point from like starting off this way and coming up with the formula after this. So we have the mechanical energy initial, which is equal to mechanical energy final. So we have K initial plus UG initial is equal to K final plus gravitational potential energy final, right? And we know that in the beginning, because it's on the floor, the gravitational potential energy is 0. And when it's at the peak, okay, because it's not moving forward, it's just moving upwards, the kinetic energy is 0. And so we have an equation that looks like this. The kinetic energy initial is equal to gravitational potential energy final. And we can break this down even more, right? When you're trying to solve for things, 1/2 mv squared is equal to, this will be initial mg h final, right? So if we were to come up with a graph for this, we will come up with a energy versus time graph, and the time will of course be in seconds and the energy will be in joules. And so if we take a look here, we know that in the beginning it's all kinetic energy, and that kinetic energy quickly turns into gravitational potential energy. So if I remember, I use red for gravitational potential. And it's going to follow that same shape. So we have a gravitational potential energy down here, okay, and as it goes up in height, we get this beautiful kind of little curve right there. Okay, so we get this kind of petering out effect, and the inverse of that, which would be the kinetic energy graph. Okay, kinetic energy, and we will get the inverse. So it looks something like this. Pew. Yeah, I should have drawn that a little bit better. Let me do that better. Pew. All right, yeah, that's good stuff. And of course, the most important part, the mechanical energy. And that'll be constant throughout as long as there are no outside forces. Ta-da! All right, now this is what it would look like for an object that is launched. And here's something cool. So if we were to combine the graph that we just drew, a launched object versus a dropped object, we can see what it would look like for an object that is to be launched and then fall down. So if we were to just superimpose the graph over here on the right hand side, but just so that you can see that, we'll draw that out. So we have, let me get that a little bit straighter. So we have energy in joules, and then we have time in seconds. Okay, so we have a object that is going to start off on the floor, goes pew, goes up, and then whoop, falls back down to the floor. So let's do the total energy first. Because the total energy will be constant throughout the entire drop, assuming that there's no air resistance. Alrighty, and then we are going to do the potential energy one, right? So we did potential energy in red, so I'm going to zoom in a little bit here. So potential energy, which is going to be in red. First, we start off with no potential energy, okay, and then we shoot up, and we reach the peak. So right there, that's our peak point. I'm gonna mark that. You can see this is the peak. Okay, and then it falls right back down. Oh yeah. Okay, so the energy, the potential energy, it increases, and then at the peak it has its max, and then it falls back down. And the inverse is true for the kinetic energy. In the beginning, when we first launch it, it has the maximum amount of kinetic energy. I just want to show you where the peak is. So right there, this is the peak. It's the maximum amount of kinetic energy will be here, which is the total energy, the mechanical energy, and then we're going to kind of curve that out right there. Okay, so I want to make that a little bit more curvy. Oh yeah, that's a good curve, right? And then it kind of flattens out, or it goes back in the inverse direction, like so, right? So we can see that at the peak it had its maximum, or excuse me, at the peak it had no energy right there. So let's just kind of do that to be 0, right? And then here we see that it has the maximum amount of energy there. A couple of zeros here is it starts off with a gravitational potential energy of 0, and it ends up with a gravitational potential energy of 0. And what that means is that it just hit the floor. It hit the floor. So I'm just gonna create my labels because labels help. This is my mechanical energy. Okay. All right. So if we see this graph here, we can see that this graph that we just drew is just a combination of the other two graphs, and that is for an object that is being launched up and then falling back down. All right, so let's do a quick recap. The biggest idea, the most important idea is right here. Energy cannot be created or destroyed, only transferred. And the way that we represent that is through the mechanical energies. Okay, so we create a formula called the mechanical energy initial is equal to the mechanical energy final. And we list all the types of mechanical energy that can exist. Now this equation, it can change in the future, and we will change in the future when we add in work. Ooh, okay. And then an important idea here is to identify what your zeros are. That really, really helps, especially with the word problems. It cleans things up very nicely because we have like a giant equation there. If you have any zeros, make them zeros. It just makes your life so much easier. And then we also took a look at the graphing. Now, the graphing is what's important here because they often like to use multiple choice for graphical questions. And know that the most important part about this is that it has this curved shape for objects because of this v squared, and also the mechanical energy is constant. The mechanical energy is constant. Alrighty? Okay. And that's it. I'll see you next time. Bye-bye.